Right. So in the last class, we discussed about that the catalysts, that is your transition metal catalysts, which means they have variable oxidation states. And based on that, they have many applications uh, in this electrochemistry based reactions, and in some of the reactions where we find that this catalyst in fact is helping to change the oxidation state. Otherwise, it's not possible to have the reaction. I'll show you the examples. Before that, we start with vanadium. And can you remember that previously we discussed with iron, huh, and copper, right? In the last class, or okay, just for a quick review, I'm just going back to the previous lecture and coming back because this is linked to that. All right, just wait 1 minute. Transition metals. Okay, done. All right. So you can see that, right? So in the last class, we discussed these transition metal compounds as that catalyst. So these work because of their ability to change the oxidation state. So we have to choose that what should be our catalyst. In this case, reaction between iron 3 and vanadium. So where is that iron 3 and vanadium? You see that this is 3 plus 3 V3 plus, right? Now, how can they react, right? If it is so, then we bring the your one of the catalysts which can change the oxidation or your state of this your reactants. So if we choose copper ion, cupric ion, Cu2 plus V3 plus will have Q plus ion plus V4 ion. So you've seen that the vanadium 3 has changed to vanadium 4. Vanadium plus 3 plus has changed to vanadium 4 plus. Now Fe3 plus ferric ion plus this copper just generated from this, right? Because we have chosen cupric ion. Now Q plus ion has been generated. So this is acting as a catalyst because this one will be cancelled. Can follow? This Q plus ion will uh, oxidized or reduced. Reduced ferric will be reduced to ferrous. Okay, and Q plus ion will be oxidized to cupric ion as before. Fine. Then you will have overall reaction will be ferric ion plus vanadium 3 ion. All will be cancelled. Now ferrous ion is reduced, iron is reduced, and vanadium 3 plus is oxidized to vanadium tetra. That means V4 plus, right? So this way we have transition metals to act as a catalyst. Same thing goes with this. Suppose iodide ion and thiosulfate. So how can it be that that negative ions repulsion will occur because this is iodide negative and this is also negatively charged? How can it be that they will react? Oh, so we bring such a compound that will change the oxidation state of these reactants. Then it will work. For this, we have iron. This is acting as a catalyst. Previously, iron was acting as a reactant. Now, iron is working as a catalyst. So we have taken ferrous ion. Hmm. Now, ferrous ion will change the oxidation state of the reactants, and here we can see that Fe3 plus iodide ion, because this is another reactant, right? And this is just generated. Originally, we have taken ferrous ion. Now it has converted to ferric ion. Ferric ion will react with iodide ion to produce again ferrous ion, and iodine. Free ion will be liberated. Now iodide, the oral, will be sulfate ion and iodine, right? Free iodine. So this way, the reaction is carried out by using the transition metal as the catalyst. All right, so we'll see some of the other transition states, other catalysts that will act as the uh, e- electrochemical catalysts. All right, right. So now, vanadium oxide catalysts used in the contact process for the manufacture of sulfuric acid. Sulfuric acid is a very important chemical uh, in our everyday life. We use sulfuric acid for a lot of things to produce. Sulfuric acid itself can be used as a catalyst for other cases. Uh, So now, during the contact process for manufacturing sulfuric acid, we are now producing sulfuric acid as a product. However, this sulfuric acid itself can be used as a catalyst for other reactions to carry out. Uh, However, so during the contact process for manufacturing sulfuric acid, sulfur dioxide has to be converted into sulfur trioxide. So this is done by passing sulfur dioxide and oxygen, both gases. So this is homogeneous reaction over a solid, but again this is heterogeneous because this one over vanadium catalysts. Right? So sulfur dioxide and oxygen using this vanadium pentoxide, we are getting sulfur trioxide. So it is a good example of the availability of transition metals and their compounds to act as catalysts because of their ability to change the oxidation states. Now, sulfur dioxide is oxidized to sulfur trioxide by vanadium pentoxide. So in this process, vanadium 5 V2O5 is oxidized is reduced to V2O4 itself, and is SO2 is oxidized to SO3. So vanadium 4, this one, vanadium 4 oxide, is then reoxidized by oxygen to form its original form, vanadium pentoxide. So this is a good example of the way that a catalyst can be changed during the course of reaction. Catalyst itself will change the oxidation state of its own oxidation state. It will change the oxidation state of others. Later, it will get back to its oxidation state, and will be removed from the reaction as it was before. So this way the catalyst is working. So at the end of the reaction, though it will be chemically the same as it started, so it will be recovered as the catalyst, because we need to get back the catalyst and to use it again. Now, homogeneous catalysis, this is the catalyst in the same phase as the reactants. Typically, everything will be present as a gas or contained in a small liquid phase. The examples contain one of each of these examples of homogeneous catalysis is that the reaction between persulfate ions and iodide ions. This is a solution reaction that you may well see in the context of catalysis. So, persulfate ion and iodide ion, right? So are very powerful oxidizing agents. Iodide ions, just we saw it before, I think, right? So iodide ions are very easily oxidized to iodine, and yet the reaction between them in solution in water is very slow. So if you look at this equation, it is easy to see why that is, because this one negatively charged ions. So how can it proceed? So we need to change the oxidation states of these. Then it will react. So the reaction needs a collision between two negative charges. This is negatively charged. This is also negatively charged. So repulsion is going to get seriously in the way that it's going through. The catalyzed reaction avoids that problem completely because it will change the oxidation states of these reactants. The catalyst can either be iron 2 or iron 3, ferric or no, ferrous or ferric, which are added to the same solution. So this is another good example of the use of transition metal compounds at catalyst because their ability to change the oxidation states. So the persulfate ions oxidized in the iron 2, that is ferrous iron 2, ferric ions. In this process, the persulfate ions are reduced to sulfate anions. Okay. So, okay. So the iron free are strong enough oxidizing agents to oxidize iodide ions to iodine. In the process, they are reduced back to iron 2 again. Right? Both of these individual stages in the overall reaction involve collision between positive and negative ions. Now you see that here we have changed your oxidation states. So we'll have these positive and negative ions to react, and then we'll have our product. So this will be much more likely to be successful than the collision between two negative ions in the uncatalyzed reactions. So catalysts accelerate reactions and thus enable industrially important reactions to be carried out efficiently under practically attainable conditions. So very often, catalytic routes can be designed such that raw materials are used efficiently and waste production is minimized. We do not want waste, right? We want our products. So if we have a lot of waste, is wastage of our chemicals as well as it's that disposal problem it's bringing, that is waste disposal problem. How, where to, this is waste, right? We need to either recycle it or use it in another way. Uh, but wastes are not desired products. So we need to use catalysts to minimize this waste production, whereby we wish to get more products, our desired products. So roughly 85 to 90% of all products are made in catalytic processes, and the percentage is rapidly increasing. So we can see that some of the heterogeneous catalysis. Catalytic cracking of crude oil. We use zeolite as that catalyst. Hydrotreating of crude oil. So cobalt molybdenum, nickel tungsten. So all these are used for hydrotreating of crude oil. Forming of naphtha to gasoline, platinum compounds, other compounds. Oh, so it's that we use different catalysts together with this. Previously, we have seen that platinum, rhodium, your palladium, right? So this has got dual functions. Platinum will play one role, the other part will play another role. Alkylation, we have sulfuric acid, hydrogen fluoride, solid acids as the catalyst. So you need to know what are the catalysts and what are the reactions involved. We cannot memorize all these, but we can have a good idea on that, right? Suppose if you are working in any petroleum company, definitely they will have this catalytic cracking. They will have this refineries products to be used, which means you will have the petrochemicals to produce from this petroleum resources. So you will be using the catalyst. So what type of catalyst will be using? If you see that here it is zeolite for catalytic cracking of crude oil to produce this your uh, small fractions of these long chain molecules. You have reforming of naphtha, that is your formation of cyclic compounds or getting it with other shapes of this. Hmm. Alkylation also is that alkylation. This is different. This is in any industry can use this one, whereby any alkyl group is added to this long chain of hydrocarbon. So this is alkylation. So in alkylation, we can use sulfuric acid, hydrogen fluoride, solid uh, acids catalyst, and boron trichloroethylate, right? So these are the catalysts that are used. So polymerization of ethylene, propylene, aromatic compounds. All these use this chromium, either chromium or titanium chloride over magnesium chloride. Ethylene epoxide to ethylene oxide silver can be used as that catalyst. Vinyl chloride, copper is used as copper chloride is used for vinyl chloride. So this way, steam reforming of methane to carbon monoxide and hydrogen using nickel, water gas shift reaction, iron oxide, copper, zinc oxide is used. So ammonia production, methanation, all these using nickel, iron, right? This way, a lot of catalysts are used to expose this one to you to have just a little knowledge on that. Suppose ammonia synthesis, they use iron as the catalyst. So ammonia is why it has got a lot of applications. It can be used as a fertilizer, right? Ammonia directly can be sold to cold countries. Liquid ammonia in the form of liquid ammonia, and they directly discharge it into in the soil, right? So this is the good source of nitrogen and hydrogen, right? So it will decompose into nitrogen and hydrogen, and plant will get this nitrogen from this ammonia. Ammonia can be used to produce urea, where we use in our tropical countries this urea as that fertilizer. So there they use iron catalyst. If you have any opportunity to work in this fertilizer company, definitely you will come across with this reaction with this iron, right? Ammonia. Previously, I was working in a fertilizer company. That's why I'm telling you that uh, this one, that is uh, your for the production of your urea, we use this ammonia. To produce this ammonia, we use iron. Now, ammonia oxidation to NO and HNO3, platinum, ruthenium, okay, acrylonitrile from propylene and ammonia. We used two different heterogeneous catalysts. That is bifunctional catalysts. Two catalysts, bismuth and molybdenum, iron, and SB, that is bifunctional catalysts. Hydrogenation of vegetable oils, nickel catalyst is used. Remember this type of thing. That is, if you are using in the food chemist, your in anywhere where you are converting this double bond into single bond, can follow. Hydrogenation, which means addition of hydrogen. Hydrogen will be added to where you have double bond. Double bond will be broken to single bond, and this hydrogen will be added. Otherwise, if it is saturated one, how the hydrogen can be added? So there must be unsaturated one, that is double bond or triple bond, where we can add hydrogen. To add this hydrogen, we need a catalyst. So usually nickel performs good to absorb hydrogen and later release it. Previously we have shown the mechanism, right? Sulfuric acid can be for this production we use vanadium pentoxide. Just now we have seen that one. Oxidation of carbon monoxide hydrocarbons use platinum, palladium, reaction of NOx. It is also platinum also. It's not written here, but we have previously seen that. Vanadium oxide, okay. uh, RH, that is your ruthenium and platinum together, and also palladium also used, platinum and palladium for this carbon monoxide conversion and the hydrocarbon unburned hydrocarbon conversion in the catalytic reactor, catalytic converter. Now we have autocatalysis. In autocatalysis, the reaction is catalyzed by one of its products, which means autocatalysis do not be confused with automobile catalysis. That is your in the exhaust pipe of the car or motorcycle we have this catalytic converter. This one not catalysis. This is automobile catalyst used for automobiles. Sometimes we hear this term auto catalysts. uh, is it referring to automobile? Yes, at that time it will refer to automobiles, because auto catalyst, we are used talking about auto catalyst. But when it is auto catalysis, this term giving us the impression that this is the catalyst automatically generated. And follow me, the catalyst is automatically generated. That means we do not need to add any other extra catalyst, but it's being generated from the reaction, from that your reactants. It's just forming a product, and this product is immediately acting as the catalyst. This is autocatalysis. Hmm. But if you hear the term autocatalyst, then refer to your automobile catalysts. So, okay, this is also can be termed, I'm not very sure, that is whether we can call it as auto catalysts here, because this one is in fact is generated from the reaction. So this term, in this autocatalysis, we are getting one of the products acting as a catalyst. So the reaction is catalyzed by one of its products. One of the simplest examples of this is in the oxidation of a solution of oxalic acid by acidified solution of potassium manganate. So we have the reaction is very slow at room temperature. It is used as a titration to find the concentration of potassium manganate solution and is usually carried out at a temperature of about 60 degrees centigrade. Even that, it is quite slow to start with. So the reaction is catalyzed by manganese ion. Manganese ion, just when it's produced, immediately it speeds up the reaction. So this is acting as a autocatalyst. So there obviously are not any of these present before the reaction starts. We did not take any additional catalyst. It's just generated from the reaction. So it starts off extremely slowly at room temperature. However, if you look at the equation, you will find manganese 2, this manganese ions are amongst the products, because this is one of the products. Later it will act as a product as well. So more and more catalyst is produced as the reaction proceeds, and so the reaction speeds up. As you are producing this amount, the higher it's being produced, the we find that the reaction is accelerated, which means it's acting as a catalyst. Okay, so you can measure this effect by plotting the concentration of one of the reactants as time goes on, because with the passing of time, the reactant concentration of the reactant is coming down, is falling, right?